Buenos dias. Thank you for showing up to my talk, Advanced Fuzzing with LibAFL. I'm Dominik Maier. I'm from Germany originally. I'm maintainer of LibAFL, which is the fuzzer I'm going to talk about, and AFLplusplus, which is another famous fuzzer. I work at Google at the Android Red team, where I'm looking for bugs and using this fuzzing, for example, stuff professionally. And I do some Rust on the side. LibAFL is also written in Rust. Right, this talk I'm going to give a quick introduction to fuzzing. And then we're going to talk about LibAFL. We're going to do what to do with cool fuzzing things, and I give an example how to fuzz an Android library outside of, like, on a host machine. And then we can see where fuzzing can go in the future as well. The target audience is like anything from somebody who has never seen a fuzzer to somebody who thinks they know everything about fuzzing. And then also feel free to ask me more questions after the talk. Right, AFLplusplus is a fork of the original American fuzzy lob, hence the rabbit. It's an American fuzzy lob. It started in 2019 when the original author of AFL basically kind of stopped maintaining it. We are members from all over Europe that work on this open source tool. We added a ton of community features in the beginning, and then since then have continuously advanced the state of the art. And we started exploring fuzzers outside of plain old AFL. This is why we started building a library to build fuzzers that are more super flexible. What is fuzzing? I mean, you made it to this talk, so probably you already know something about it. But in a nutshell, you just run a target over and over and over and over again until it crashes. And you make that in a smart way, somehow. So you try to find usually crashes, but we can also find other things that we're going to discuss later. And the smartest invention in this space in the last 20 years probably was coverage-guided fuzzing, or feedback fuzzing in general, which is I run the target and I observe the target and see if something changes inside the target, and if it does, then that's nice, I found something new, and I want to find something new. It's a novelty search algorithm. So basically, in a control flow graph like this, I go left or right during the execution of the program. So if I have an if statement, the program at runtime either jumps to the left or jumps to the right. We count how often each of these jumps happen. And if we find that one of these jumps happened a different amount of times, or we find a completely new branch, then that is nice. We found something new. And we keep track of new coverage, like inputs that reach new coverage, to mutate further in the future. This way, we're orders of magnitude faster than just plain like randomness to an input. So for example, this is how like this would look in code, right? You go through the feedback map, which is basically a map that tracks every single edge axis. So if the jump happens, we add some code, instrumentation, that increases a map at a counter. So we have like a hash from this edge to a place in the map. We increase the size of like this counter, and if the counter is different, in this case, larger than before, so we saw this branch more often, which means like something happened in the meantime that's interesting, then we say we want to keep this input for further mutations. Sweet. Exactly. Yeah, that's the one I was just talking about. And then we implemented a lot of different like feedback mechanisms, etc., inside, as I said before, LibAFL, which is the advanced fuzzing library. And it's fast, scalable, portable, blah, blah, blah. I don't have to go through all of these because we're going to go through some of them in depth. High level, we have like the main LibAFL thing, and we have instrumentation stuff, which is injected into the target to collect coverage information, etc. We have a compiler wrapper, and then we have multiple instrumentation backends like that I'm also going to go into it. This is the architecture in Lego, because Lego's nice. Basically, this is the feedback that we talked about. Here, we look at how the target execution, how it behaved. We observe the target, and then if we found something new, we store it into the corpus for future mutation. The future mutation gets done by mutators, and then we have multiple ways to execute the target. So far, so good. Sweet. So how do I fuzz what? So a simple command line tool, I mean, that's like the most simple thing that you can find is a file, open, read a file, do things with it, and then exit the tool. This is super easy to fuzz, right? We basically compile it with like instrumentation. That's the thing that adds information about which edges has been taken, etc. And then we execute the target over and over and over and over and over again, providing a different input to the tool every time. We can do this. So what we do is basically we have a fork server for that, so we don't restart the program from scratch, but instead at main, or even at a later point in the program if you want to, we fork the program so the memory gets copied to a different process, and that makes certain things easier and faster, but basically we don't have to initialize the whole program anymore. Of course, this is super simple, fast to set up. Every execution resets the complete program to the beginning, which makes it reproducible if your target doesn't read from random or do things according to the time of the system or something. Of course, then it's not reproducible. Problem is we fork every single time. It is very slow. The kernel has to do a lot of page table stuff, and it doesn't scale well because the kernel isn't really made for scaling like forks to 64, 48, whatever cores, 128. So if possible, we want to do something else. Well, what else can we do? Oh yeah, this is the fork server executor, like a nice thing. What happens? So we have our fuzzing tool here. The fuzzer has IPC to the harness, or to, in this case, just the main function. And that runs like forks every time, runs one execution, forks again, runs one execution. We can also keep the target running for longer, but that's the way usually a fork server works. Right, but if we fuzz a library, for example, we don't have like this main function, and it has a simple API, and ideally the library can be called multiple times in a row. Usually you don't have to restart a library to like reset the state. It has like some sort of, depends on the library, of course. But the nice thing here is we don't have to fork. We have one function that receives data from the fuzzer, and then it runs that library, and it collects the coverage, and then it just returns back to the fuzzer and then gets called again. This is super simple. It scales because it doesn't need any IPC and nothing. It is very fast. Problem is when the target crashes or timeouts, which is of course like for us as a fuzzing people, we already found something interesting in this case, so we're kind of almost there. But still, if the target crashes, then either you lose all your states that you like, if you have multiple things in your, like your corpus grows, etc., suddenly the thing crashes. So what do? Everything is gone, right? Or you have to, what we do in LibAFL, have a very dirty signal handler that catches the crash or the segfault or whatever, serialize all your data to like some shared memory region, exit, restart, deserialize all the state, and continue running, which is an issue. Like it's definitely slow, right? So in the best case, it's very fast, and in the worst case, it's very slow. Sweet. So yeah, if you think back of the fork server executor, this is how it looked like. And now we have an in-process thing where we can run over and over and over and over. Cool. So smart idea. A command line tool can also is basically a shared library. So we can also use this in-process fuzzing for a command line tool. This has the same pros as running a library. Problem is we have to reset the state for the tool after each run because it may not assume that it can be rerun from like the main function without exiting. So there's more engineering effort, etc. Sweet. Well, then there are some things in between, which is basically fork every execution but be in process, or have keep the fuzzing running but have an IPC between. But that's just for to give a full picture here. Okay, now we can execute. Now what do we do with the execution? There is normal AFL style mutations, which are just basically random byte bit flips, random byte increments, decrements, etc. And this is the thing that most like fuzzing things should start with. Just do whatever you can be stupid about it, but be super fast. This needs no knowledge of the target. But it also doesn't have any knowledge of the target. So if it's more like crazier, harder to mutate, like input the structure, it's going to be hard. Sweet. This is a simple mutate. It just mutates one byte. And then these mutators can be stacked. So one input, we wouldn't run one, like mutate once and then run the thing, but we mutate like hundreds of things on top and then execute the target. So like more randomness can happen. And then we also have like schedulers that make smart decisions about what to fuzz. Sweet. So basically, the mutational stage is like a thing that mutates. It loads an input. It like creates a new instance of that input, mutates it, executes the target, observes the execution, and looks at if you found something new. If we did, cool. All right. So, but not everything takes raw bytes, right? There's a lot of very, very crazy input problems that we have. Think of a JavaScript engine. Think of even XML. Like if you open the tag, if you change the open tag to, like if you change one byte in there, you have to change exactly the same byte in the closing tag, else the parser, I mean, it will do something, but it will not accept this as valid XML. So these things are hard. What about a library that takes more than one input? Like if it's not just parsing a single bytes thing, but like multiple. And what are targets that are like reading from a file and from standard in at the same time or something like that, right? Or a server that needs multiple connections to do what it needs to do. Sweet. Well, we do have like a lot of examples in our repository. And one of them is structure-aware things. And then we can go into how a fuzzer can find its way through a program better if it's not only single byte mutations. So the one, let's start with a very simple idea, or like a beautiful idea, but it's simple to explain. Basically, assume we have two 64-bit values, or like one 64-bit value that the binary compares against. How long would it take to brute force this 64-bit value? If you've ever done any password cracking or something where you only spend time on this 8 characters, you know it's going to take like 700 million years, I don't know, like long. But in this case, the fuzzer doesn't only mutate this 64-bit value. It mutates all of the input. And mutating this 64-bit value is like unlikely as depending on how big the input, like it can mutate something else for one execution. So it won't even spend all its time doing that one single input, right? And it would also not get there directly, but it has to go through all of the program first, right? So what people have done, smart people, is they implemented basically instrumentation where every comparison is just split into multiple single byte comparisons. So instead of if like 8 byte equals 8 byte, you do if 1 byte equals 1 byte, 1 byte equals 1 byte, etc., etc. So that way the fuzzer gets like a coverage input, it finds a new edge the moment it gets one of them right, which makes it a lot easier to get through. Problem is that the corpus grows a lot because every single input is like eight times the amount of potential inputs. And then later in the time, it's going to be hard to find the right input again. Like progressing will get harder over time. Sweet. Another thing is we can have token files where we give, like in the XML example, we give it valid XML tags. And it can then go ahead and insert valid XML, like these tags from the file that as a user we know, and insert them into random places. So if we have an open and close tag in this file, it's more likely to put the open and the close tag in like potentially the right places. This is very simple. It doesn't need like me to understand much about the target, but also on the flip side, it doesn't really know about the target itself, so it's like super randomic still, but it does help. And then we get like down the rabbit hole. We go to basically tracing execution at runtime of the target and looking at comparisons at runtime. So if we see that dog and cat are like the two things that this binary compares, and we know that we have like in our input we have a dog, and we see that there was a comparison between cat and dog, then we rerun the input, replacing this one input, this like dog with cat, and see if we can get to new coverage that way. And this is this works super well. Like it's still reasonably fast. I mean, it's of course way slower to like log all of the comparisons, but it's still reasonably fast in comparison to like full on like symbolic execution or tracing. It's slow as a contra, but only in comparison to not doing this. But like you get a lot more like precise results that way. Sweet. And then you can go away from just bytes. We start going to like abstract, more abstract inputs. For example, there's token level fuzzing, where let's say I want to fuzz JavaScript, and I basically read a bunch of JavaScripts as input. So I have like a corpus, a good input corpus with a lot of different JavaScript that I know is like weird and can trigger cool behavior in the target. And then instead of mutating every single byte, and in this case, if I mutate like the equals, like it's not going to be valid JavaScript anymore. The parser will just say, well, you're stupid. I'm not going to do anything with your input, right? So instead, we parse on loading. We parse the JavaScript. We tokenize it, and we assign IDs to every single token. And then we don't mutate the bytes. We mutate the abstracted input. So we mutate, the IDs basically. So we would shuffle these around. We would use IDs from other inputs and put them in here, for example. Right. So this is pretty smart. It is still simple to build because all you need is like a good corpus of inputs. And the only issue, one of the issues, is of course that this will never find something you didn't have in your initial input. So if there's like a JavaScript function that's not specified anywhere and nobody has this in their input corpus, this will not find it because it will not randomly generate anything. It will just mutate like according to these things. And then we can take this idea even further. We can do structure-aware fuzzing, where basically I know that like an API call takes a struct, or like I know that it has like 3 vectors in 3 different places, and we have like APIs for that that tell the fuzzer to please mutate these 3 vectors, but keep them to be vectors, or like there's an optional value, like turn it on and off randomly, these things. And that is pretty cool. It's a bit hard to get going for like if you have deeply nested structures that need like weird vectors that can grow in size, etc. It's like a lot of engineering that has to go into this to be really, really good, but it works pretty well. And then similar, but somehow different, you can also specify like a grammar of the input space to the target. So I would say, I know that, like how a JavaScript, or like in this case here, I don't know if it's probably too small, but this is a statement. It defines a variable and then like an identifier. And then the grammar mutator would go ahead and always keep the grammar correct and mutate, for example, the abstract syntax tree inside and then make it an actual input in the end again, like make it bytes, like after mutating the higher order abstract. Yeah, sweet. And then, of course, apart from just like improving the generation of inputs, we can also try to get like better information back, which is similar to, or like basically Complog is one instance of that, where we know that a new state in the target has been reached, and the state is interesting, and we tell the fuzzer through a custom feedback, hey, you found something cool, keep that to future mutation. Yeah, because like if you think of JavaScript engines, the code that they execute looks the same from like a coverage perspective, but the actual code that gets run, like there's a lot of state that you don't see in coverage, like which part, like in an object, for example, what different functions have been assigned to this object or something. That's like things that are state that you can't really measure with pure coverage. It's not a good proxy for a lot of things. Yeah. So what happens if, like nice and all the instrumentation, etc., but I really, really don't have the source code, or maybe, like in my case, it's usually the case I'm too stupid to build this because it has a weird archaic tool chain, and I need to install 20 new tools, and I don't know any of them. The nice thing is instrumentation doesn't have to be at compile time. So compile time instrumentation is like a LLVM pass or like a GCC, pass that during compilation, it like injects stuff into the compiling process. But we don't have to do it that way. We can also get instrumentation another way. There is binary instrumentation engines, and we can use the binary instrumentation engines to actually get instrumentation of a binary. I mean, that's literally the name. There is multiple ones in the world. One that I'm gonna do a deep dive today into is QEMU, the quick emulator. It's not really, you've probably not heard of it as a binary instrumentation engine, but it's basically what it is as well. It's a very popular full system emulator. A lot of people have probably already used it or maybe accidentally used it because they installed some Docker on macOS or something like that. And it supports like a super large amount of instruction sets, which makes it very useful to also fuzz targets that don't run on my desktop computer, for example. And it can do both system mode and user mode instrumentation. There's other instrumentation engines, and like LibAFL also supports some of them. Frida is one that's used a lot in like mobile contexts and is a pretty nice one. There's TinyInst, which is by Project Zero folks, which is also very similar to Frida, slightly different, but it's also good. And there is also the option to do static binary rewriting. People have done that in the past, which of course is really hard. But then it's a one-time cost. You rewrite the binary once, add instrumentation, and you don't have to do anything at runtime anymore. However, it doesn't, the runtime cost doesn't add too much because we execute the target a few 100 million times during a fuzzing campaign. So some initial cost to do dynamic instrumentation doesn't matter if it's cached well. Sweet. Looking at the binary-only options, let's get them out of the way. Just like a pro-contra list here. There's LibAFL Frida. It supports many operating systems. It's like Android, iOS, macOS, Windows, Linux, which is a lot of them. You can do JavaScript injected into the targets where you can hook things inside Java. It's pretty impressive stuff. And we have, I don't know if you've seen what a sanitizer is. I'm going to go into sanitization later as well quickly. But basically, it checks bound accesses for heap memory, for example. If I out of bounds read by 1, you can catch this with the LibAFL Frida mode. So basically, it instruments every single memory access and then checks it against some shadow map if it's a correct access or not. And we also have the comp log support here. So this is the thing that logs cat and dog from earlier. You remember that, right? The problem is it needs to be on the device. So if I want to fuzz Android, it needs to be on Android. If I want to fuzz iOS, it needs to run on iOS. I can't rehost easily, at least, to another device. And then there's TinyInst, which is the Project Zero thing, which has also at least Android, macOS, Windows, Linux support, I think. And it can split comparisons, but it cannot do comp log. And now let's go into the QEMU mode, which is the fun one, I think. It is very actively developed, cross-architecture, and has cool stuff like you can S-trace your target, you can GDB step through it. And it also has address sanitizer, comp log support. But this thing only runs on Linux. So it can run a guest operating system that's a non-Linux, so it could run a real-time operating system, but it has to run on a Linux host, which sometimes is I walk around with the Mac in the plane, and it makes it a bit harder. And there's runtime overhead, of course, because you do binary translation. But overall, I really like QEMU mode. It's a good stuff. And where does the runtime overhead come from? How does QEMU even work? What's the internals of QEMU? I don't know if you've looked into that before, but it's really cool. Basically, it goes basic block by basic block. It disassembles this one basic block, lifts it to an intermediate representation, which is similar to something that LLVM uses when compiling down, but instead it does it the other way. It takes the bytes and lifts them to an intermediate representation. And then it compiles, or not really compiles, I guess, assembles or something, I don't know. Like it drops that intermediate representation back down to the host, like, target architecture. And as I said earlier, in LLVM, we can do intermediate representation stuff to get instrumentation. And here, we have an intermediate representation again. So also here, we can do instrumentation. And that's the fun part, where the fun begins. So we take a basic block. We look if we've already seen that basic block. If we've not seen it, then we generate, we generate the intermediate representation, and then we can add our own LibAFL stuff inside there, and then it gets run with our instrumentation. Sweet. So we can instrument targets, but I said it's full system, right? So can we do full system stuff as well? Yes. People actually do this, like they run a full operating system inside an emulator or an VM, of course, and instrument the target somehow, in the QEMU case with QEMU, and then inject input into the target. So basically, for example, you could have like a little agent running inside the VM that then calls a syscall in the kernel or something. Or you can also do like IPC between different like Firefox processes, where you would, instrumenting a single process would be super hard. That would be super easy. Instrumenting multiple processes at the same time is kind of hard, but instrumenting the full VM instead is easy again. I mean, it's obviously not easy, but like it's doable. And apart from the QEMU mode, there's also Nyx mode, which is instead of emulation, it actually uses like virtualization and Intel PT tracing, etc., to get coverage of the target. It is a lot faster, but it doesn't work cross-architecture, and it's complex with a K because I'm German. Sweet. And the other option to do a full system emulation is we can do, instead of running a full operating system, which of course is slow and we need to understand a lot because we need full introspection into what threads are running, etc. What is also nice is just copy-pasting a single blob of bytes into our emulator and then just running one function. We can even do it, we can assume it's like a user mode application at this point. And that way it is a lot faster because it doesn't have to run a full operating system, and it's also easier to understand and build, for me at least. But then you don't have, if it's like an embedded system or something, you don't have the state that would, the emulator would boot up the whole thing, and then you would have like all the allocation stuff is set up. You can actually do IPC calls to other tasks, etc. All of this is not possible if you only fuzz a single target. But it's a nice option as well. Sweet, let's do some fun examples. LibAFL QEMU. It's, as I said, we can add hooks. As I said, we can add instrumentation. And this instrumentation can be hooks, for example. Like the normal one is edge hooks. That's the one, like every single edge gets instrumented, and then we can keep track of coverage. But we can also do comparison hooks, where we hook every single comparison, and we can do something with the target at this point. Like for the fuzzing use case, of course, as I said, we log the comparisons, but we could also go further than this and basically do anything with the target because it's an emulator. It's like you're around it and do whatever you want with it. So you could also change the result of comparisons to get to edges that you would otherwise not reach or something. There's more hooks. You can hook syscalls, you can hook crashes, obviously, because you want to see that crashes happen, new thread creation in user mode, etc. Sweet. You can interact with the thing with GDB, and LibAFL uses the, So the way the target can interact with the emulator is through special calls, basically to the, hypercalls, kind of. Think of hypercalls. Like one that says, I'm done with coverage, I'm done with the test case, give me the new input, for example. So then you can do this over and over again here. So basically, you run something, and then the target can say, I'm done with running something, give me the next input. Do this over and over and over again. All right, so this is code. Welcome, code. The LLVM test, fuzzer test one input or whatever, was the function that we saw in the beginning with the in-process executor. where we get bytes and a pointer to like a bunch of bytes and the length. And in this case, we load an elf with our little elf loader, and then look for this symbol inside the binary, because it's a binary only thing, but we have symbols this one. And then we write a harness that basically gets the inputs from LibAFL, the bytes input in this case, so it's like not super advanced AST stuff, but it's just the byte input, and then writes to the input address the contents of the buffer, and then sets up RDI, RSI, RIP, RSP, so all of the, basically sets up the state to run the function a single time. It runs the function and returns, okay, I ran the function. And then this gets called over and over and over and over again until hopefully the thing crashes. Or hopefully, I mean, depends like on your use case. Right, and then we have like the coverage helper, the coverage helper that basically collects coverage. It's renamed to coverage module recently, but it's still old. And then we can run it, and it runs with like hundreds of executions and hopefully find crashes. We can do this for a cool target. So let's look into how to run an Android binary on Linux and find bugs there. There was this Project Zero blog post a while ago where they looked into the Samsung Q-match codec, which is like a weird Samsung codec that can be used as a remote attack surface. So basically, you send somebody an MMS, and the MMS parses this image, if it's a Samsung phone, and crashes the phone if it's unpatched from back in 2020. Right, there was like talks about it, etc. So once you reverse this thing, you find the interesting pointer. This is get image info from file, which basically gets the image info. And as we know from like previous work, is that this one is broken. So we write a harness, which is basically the get image info. So we figure out in IDA or in Ghidra or in Binary Ninja how the function signature looks like. And then we write a harness, which takes input and then passes this on to the right function. And then we use the LibAFL QEMU stuff to load the target into LibAFL QEMU. We hook all the syscalls, so the library is not going to do any outside world communication. It's just going to be talking to our emulator. If it like wants to read a file, it reads a file from us instead. If it wants to like get a random number, it gets like a non-random number, because then we have a perfectly repeatable execution. And that way, it is very, 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 very fast, because it doesn't have any kernel interaction. Right. So this is a very simple fuzzer yet. We set a breakpoint to the harness, and then we run it until there. And then we end up here. We write the input to file. It's not a real file. In a perfect fuzzer, like in this case, it writes it actually to disk, but later we replace it with like our hooked syscalls, so that it doesn't actually read from disk, but it reads from our cool harness, and it's faster. Oh, and we have a snapshot restore that we're also going to talk about. Sweet. So more helpers, doesn't matter, I think I'm running out of time. Yeah, we hook the syscalls. So if it's a write, we just return, yeah, you wrote all the bytes, because nobody really cares and nobody's going to read it anymore. And then if there's like 2 or 3 other syscalls, like sigprocmask, that we just return like a dummy value, so it doesn't have to actually hit the kernel. And then the simple one was 5,000, and I think the good one was way, way faster. But maybe I don't have the screenshot. Oh, yeah, I have it. Right, and this is okay, I'm getting to the more complex fuzzer. I'm getting ahead of myself. We can do snapshot fuzzing, which means that instead of running the same library over and over again and having to manually reset all the state, that like if it allocated something, we don't have to manually free it, but instead we do a snapshot of all the address space, and then the fuzzer automatically keeps track of touched pages during the execution. So it does dirty page track, basically, and after the run only resets the dirty pages, which is pretty fast. And then we add address sanitizer. That way we get heap corrections. There's not really a good way to do any sanitization on the stack. for binaries because we don't know where variables start and end. But for the heap, we can see what an allocation looks like and a deallocation, and then we can track like the lengths and stuff and then poison the bytes before and after the allocation, for example. Right. The snapshots, how they work, is they hook memory writes and track dirty pages. So every time the target writes, we add this to the change data, and in the end, we reset everything. And we also have to do that for syscalls that interact with memory. So if the target mmapped something, we have to un-mmap it for the next execution again. Right. So we reset everything. A sanitizer tracks all memory accesses, hooks the known libc and allocation function like malloc free, the copy by string copy, etc., and crashes in out of bounds accesses, use after freeze, etc. And right, so this is the more complex fuzzer now, where the image codec gets like read and then executed. I think, yeah, this is just like, if you have more questions about it, feel free to approach me. But right, so we get the stack pointer, we get the return address, we read the memory for the stack pointer, and then we run there, map like places for our input, place our input, and then we can go. Sweet. Something moves. So yeah, we basically copied the whole system to the host. So there's no Android. It's all like in the normal Linux kernel, but we copied all the libraries around. And then it runs. And that's how fuzzing looks like. Sweet. And then in the end, at some point, we find the crash inside the target. Here you see that the address is 118 bytes to the right of the 42-byte chunk. That means it's an out of bounds, which is not great. Right. And it's a write, so it's very powerful. Cool. So we can fuzz. We can fuzz almost anything, anywhere. And now, how do we get like more than one core? The thing is, the reason why I was talking so much about syscalls is because scaling is really, really hard on Linux. More cores doesn't necessarily mean more speed. This is the old school AFL, which didn't pass input to the target via a shared map, but just via a file on the operating system, and uses fork for every execution. So it's the worst you can do. But you see from 0 to around 25 cores, it scales pretty well. It looks almost linear. This is the total executions. It's not per core, it's like the total executions. And then after 25, you see that Linux does something, internally logs something, and the speed, the performance just drops. Like, it's not even funny. Like, up to between 25 and 200 cores, there's no reason to add more cores, it just gets slower. So that's not great. And that's why we created basically an IPC mechanism to share test cases between different fuzzing nodes, where we have one broker, and everything is log-free via shared memory. When a fuzzing instance finds a new test case, it reports it to the broker. The broker then reports it to the other nodes. And then suddenly what we can get is all this stuff in HTOP is green. HTOP is a tool that shows you how your core usage is. And red means it's in the kernel, green means it's in the user space. And in fuzzing, you want them to not be in the kernel, unless you're fuzzing the kernel, of course. But in this case, you want it to be green as possible. So in comparison to the AFL chart from earlier, with removing all the syscalls, what we did for the QRun fuzzing, we are almost linearly scaling to 80 cores, which is nice. This is what you want. And then we have a launcher in LibAFL that basically does all the spawning the processes for you. Like in AFLplusplus, you have to manually do it from scratch, and here it does it automatically, which is cool. And we have a broker to broker, so you could have multiple machines connected via TCP to each other. All right, and then in the end, for the example from earlier where we had 5,000 on a single core, On 80 cores, we have almost 500,000 executions per second on a binary-only target, which is fast enough. And then the question is, how do I debug anything if I spawn 1,000 of cores? There is a multiple event managers in LibAFL. Instead of the launcher, you just use like a simple one, and that doesn't spawn anything, and then you can debug, and then you rebuild the target with launcher, and it makes it like, this is the trick to actually debug the target and what's going on. Cool. Let's see what else we can do. Do we only fuzz for crashes? No, that's pretty boring, right? Like, let's hope we all rewrite everything in Rust, and then all the crashes will be solved forever. Just a little injection here. No, but for real, like, we can also try to have, for example, fuzz for injections in this case. This is an example. But you can come up basically for target-specific conditions, abort conditions, where if you reach this condition, something went wrong. What we do for injection fuzzing, for example, is we hook some functions. So, for example, in if we want to find a SQL injection, we hook SQLite exec functions, and then analyze every query and compare the query if it originated in our input. So if we find an input that goes to SQLite exec, then we found an injection, and then we crash the target. Something like this. You can build this like with, for example, binary only with QEMU, where basically you can hook all of the, even like system, you could do like system, if you find system, then you found something bad. You could also hook other things like, or change the source code if you have source code to find conditions that are not like normal crashes and make them abort. Right, so in this case we check the parameters, and then we have like basically, if we find this input, if we have multiple inputs, we find one of them in the exec, in the second parameter of exec, that's bad, right? And then this also, we can have like a little glimpse at how this looks like, if it starts. Yeah, so this is the target we're gonna fuzz. It takes an input, it has like this little exec down there, and there's, if the fuzzer finds a quote, it's an injection. It's like a super simple one. And here it found the value for select from where user X was, blah, blah, blah. All right, final words. Fuzz everything, everywhere. Builds fuzzing scalably. You can fuzz almost anything, almost everywhere, with some drawbacks. And then it's fast. Where's the future of fuzzing heading? The question is, for example, how do we fuzz servers? There's an open source tool, so people build stuff with it. The thing I recently found was really cool is whoopifuzz, which they implemented mutators for REST. So basically, they mutate REST queries to be valid REST queries, and then they added instrumentation into web servers. So they basically get state of the web server back into their target. And so you have valid REST queries to the server, and you get back the feedback for you found something new on the server. And this is a super cool idea. I think there's like something to do here. It can get even better. There's concolic fuzzing, which LibAFL also supports, but I'm not convinced it works yet, where you use the symbolic execution engine and like an old school fuzzing engine in combination with each other, but so far doesn't seem to really work in practice. Then, of course, now the LLMs are new. We can see, like, for example, the assert conditions that I was talking about, where you say, you reach a super interesting state of the program. You could, for example, ask an LLM to come up with asserts in the target that are super interesting. Or, of course, you can ask an LLM to give you like new inputs, better inputs. You can ask an LLM so many things. A lot of them it will just fail to do. But a little shout out to like colleagues that I work with. We recently found bugs in real-world SQLite code that were not reproducible by the fuzzer. So LibAFL didn't find, it found different bugs, but it didn't find these bugs that we reported found by the LLM, so that's good. LibAFL is free and open source. please like go to the repo, play around with it. There's this /fuzzers folder where there's a lot of example fuzzers, and you can usually just cargo make run or make test, and it will just start fuzzing, and you can play around with it. So that's all from my side. Are there any questions? Is there microphones? Or maybe not.
Can you use it to fuzz Go code?
So the question is, can you use it to fuzz Go code?
Go code.
Go code. So there is, you only need to get instrumentation from the Go code. I've personally not done it, but it's possible. There's also a fuzzer in Go itself, which isn't as advanced, but it's like Go fuzz or something. That is, uses very similar metrics to this, but is not as powerful. But it exists inside Go itself.
Thank you.
Thank you. You mentioned running different nodes that will fuzz different things and they will communicate things over TCP. How does that work? Because I have implemented a cluster the old way, where you have one script that can synchronize the queues. Did that change lately? It's a different.
There's old. This is old. Like it's been around a few. So basically, what it does is it opens a port, and you can also provide a port where it should connect, or like an address where it should connect to, and then when it spawns, it will connect to the other port and then share test cases over that. That has been in LibAFL for a while now. Yeah. It's like you wouldn't be able to scale this to like a super huge cluster because every node wants to talk to every node, and it could be. There's definitely improvements that can be done here, but it works.
And do you prefer to have like multiple cores or multiple servers, or is there like a good benchmark?
So the question was if I prefer multiple cores or multiple servers. I personally just run everything on like 128 cores, single machine, because it's super easy. And I'm too lazy to do real work. Yeah.
Hi.
Hey.
So I was thinking more around the thought process for figuring out these strategies. Like, for example, you mentioned edge detection, etc. And I see a lot of data structures, etc. So I wonder, how do you guys come up with the different strategies? Probably more a philosophical question, but I'm interested in the process.
So how do you come up with new ideas? It's you sit in a bar with other people that know things and you talk about that.
Nice.
It's like we can talk about it if you want. Yeah, there's a lot of ideas that people try out, and the one thing I learned about fuzzing is that your gut feeling is always wrong. Like it doesn't matter what your gut feeling is, you're always wrong. So just try YOLO, Yeah.
And try harder.
Exactly.
Thanks.
If somebody wanted to contribute to the LibAFL project, are there any specific pieces or areas of the code base that you would recommend them to get started with?
I mean, honestly, I would just get started with one of the example fuzzers and then look for a cool target that you're interested in. And then spend the time to build, like use the library to build something with the target, merge them together and hope that you find things that don't work yet and then fix them. That's, I think.
Okay, thank you.
Yeah. All right, thank you so much.